Meet John Dalton, the 18th-century polymath who looked at the sky and saw the foundations of everything. This slide, titled The Architecture of the Invisible, chronicles an intellectual odyssey spanning from 1766 to 1844. On the left, we witness the swirling majesty of the atmosphere, a nod to his foundational work as a meteorologist. On the right, we see his crowning achievement, the structured, geometric precision of the atomic theory. By documenting this empirical ledger, Dalton transitioned from tracking vast auroras to defining the indivisible building blocks of matter. Whether acting as a physiologist or the father of modern chemistry, Dalton proved that to truly grasp the vastness of our world, one must first master the invisible. Step into the meticulous world of John Dalton, where life was defined by the steady pulse of data. Guided by a Quaker ethos that prized practical observation, Dalton began his lifelong ledger in 1787. For 57 years, he acted as a human instrument, capturing over 200,000 atmospheric observations with the tools pictured here. This graph isn't just weather, it's a staggering commitment to empirical truth. Dalton's daily ritual was so absolute that he recorded his final entry just one day before passing in 1844. It's a powerful testament to a man who believed that understanding the world started with measuring it, one data point at a time, for an entire lifetime. In this visual journey, we explore the scale of observation, revealing how John Dalton's rigorous methodology remained constant while his focus shifted across the dimensions of the natural world. Through three distinct lenses, we see his scientific evolution: first, the macro, where he charted the vast complexities of atmospheric science; next, the meso, focusing on human perception and physiology; and finally, the micro, where he peered into the invisible realm of chemistry. Whether measuring a storm, a flower's hue, or an atomic cluster, Dalton's core process, counting, measuring, and categorizing, never wavered. He proved that the same disciplined mind could decode the grandest aurora and the smallest atom with equal precision. Before Dalton, the 18th-century scientific elite viewed the atmosphere through the chemical solvent theory, believing air and water dissolved into one uniform substance, essentially a giant chemical soup. In 1793, Dalton shook the beaker. With his independent fluids theory, he argued that gases don't merge, they mingle. He envisioned water vapor and air coexisting mechanically, like marbles in a jar rather than sugar and tea. This shift, published in his meteorological observations and essays, was more than just weather talk. It was the crucial mental leap that transformed the sky into a physical playground of independent particles, paving the direct path toward his groundbreaking atomic theory. It turns out, the secret to the atmosphere was simply knowing how to keep things separate. Imagine John Dalton standing beneath the shimmering northern lights, armed not with folklore, but with a homemade theodolite. In this slide, Measuring the Impossible, we see how he mathematically pinned the aurora to an altitude of 60 miles, placing it firmly in the upper atmosphere. By observing his magnetic dip needle fluctuate during these displays, Dalton made a brilliant deduction: the aurora was fundamentally electromagnetic. His relentless tracking from 1790 to 1830 even documented a significant lull in solar activity, an era now immortalized as the Dalton minimum. Through precise calculation and observation, Dalton transformed an ethereal mystery into a measurable physical phenomenon, proving that even the heavens submit to the ledger of science. Imagine looking at a pink geranium and seeing sky blue. For John Dalton, this wasn't a hallucination, it was a revelation. In The Anomaly of the Pink Geranium, we explore how Dalton's perception shifted dramatically with the light, from blue in the sun, panel A, to a yellowish red by candlelight, panel B. Never one to let a data point go unanalyzed, Dalton discovered his brother shared this trait, leading him to deduce the condition was hereditary. In 1794, he published the first scientific paper on color blindness, a condition so closely linked to him it was long called Daltonism. Once again, Dalton turned a personal anomaly into a public breakthrough, proving that science often starts with the courage to trust your own different eyes. John Dalton's quest to understand his own color blindness, historically termed Daltonism, is a fascinating tale of scientific evolution. In 1794, Dalton hypothesized that his vitreous humor was tinted blue, physically filtering his perception of the red spectrum. He was so committed to this theory that he requested a post-mortem exam. In 1844, Dr. Joseph Ransom's autopsy debunked this, finding the eye fluid perfectly colorless. The true DNA reality emerged in 1995 when researchers analyzed Dalton's preserved tissue. They confirmed a genetic mutation, specifically deuteranopia, caused by missing middle-wave photoreceptors. This journey from a mechanical filter theory to a genetic diagnosis bridges 150 years, cementing Dalton's legacy in both chemistry and vision science. Welcome to the architectural foundation of gas dynamics, Dalton's law of partial pressures. As illustrated here, when non-reacting gases occupy the same space, they behave with remarkable independence. In our first flask, gas A exerts 2 atmospheres, in the second, gas B exerts 3 atmospheres. When combined, the total pressure is the simple sum of its parts, 5 atmospheres. John Dalton observed that ultimate particles do not repel those of a different species. Instead, each gas acts as if it is entirely alone in the container. This elegant relationship is defined by the formula P total equals P1 plus P2 plus Pn. By understanding that individual pressures are additive, we unlock the ability to calculate the behavior of complex mixtures like the very air we breathe. In this exploration of the mathematics of matter, we witness the brilliance of Dalton's law of multiple proportions. By comparing 2 compounds of copper and chlorine, Dalton revealed a hidden numerical order. This mathematical perfection, expressed in small, whole numbers, provided the ultimate proof for atomic theory. Dalton reasoned that such consistent ratios could only exist if matter was not a continuous slurry, but rather composed of discrete, indivisible units. It is the predictable geometry of the invisible world. In 1803, John Dalton revolutionized science with his atomic postulates, laying the groundwork for modern chemistry. He proposed that all matter consists of tiny, indivisible particles called atoms. According to Dalton, atoms of a specific element are identical in mass and properties, while different elements possess unique sizes and masses. Dalton further explained that compounds result from atoms combining in fixed, whole number ratios, creating a predictable blueprint for substances. Finally, he addressed the nature of change. Chemical reactions are simply the rearrangement of these indestructible units. In Dalton's world, atoms are never created or destroyed, they are the permanent building blocks of an ever-shifting universe. Science is a process of refinement, and here we see how Dalton's 1803 model stands up to modern quantum reality. While Dalton's vision was pioneering, 2 of his core tenets have been updated. We now know atoms are not indivisible, as they contain subatomic particles, and the discovery of isotopes proved that atoms of the same element can vary in mass. However, Dalton's genius remains the bedrock of chemistry in 2 vital areas. His principles regarding the conservation of mass and the formation of compounds in fixed, whole number ratios remain absolutely true. These concepts continue to serve as the fundamental basis for modern stoichiometry, proving that while our lens has sharpened, Dalton's foundation remains unshakable. The origin of modern chemistry is often born in the sky, proven in the beaker. Contrary to popular belief, John Dalton's atomic theory didn't begin in a laboratory, but through his obsession with meteorology. As he studied the atmosphere, Dalton became convinced that weather was driven by a mechanical mixture of independent gases. To explain why these gases didn't settle into layers, he had to conceptualize them as discrete, indivisible particles. This slide illustrates that bridge. His macro-level observations of the clouds and pressure necessitated the invention of microchemistry. Ultimately, his need to understand the vast sky birthed the scientific framework for the tiny atoms that compose our entire world. As we conclude, we reflect on the enduring measure of a man. John Dalton passed away in 1844, a modest Quaker who lived a life of such scientific devotion that he famously claimed he never had the time to marry. Yet, his impact was monumental. Over 40,000 mourners gathered in Manchester to honor his legacy. Today, his name is immortalized in the Dalton, the official unit of atomic mass. Dalton's true triumph was transforming chemistry from mere qualitative philosophy into a mathematically rigorous science. He proved that by meticulously observing the visible, the weather and the weights of elements, we could successfully map the invisible architecture of the atomic world.